my god, I'm live. I did not realise. Hello. It's a sleepy Monday morning. Presumably people have to work, so I have to work. That's the trade-off. Let's stick on some music. This will do fine. And what are we doing today? What are we up to? I found something really cool since I last did a science stream. And that is the outer edge of galaxies. So this will take a little bit of explaining. This is a picture of a galaxy centered on the one that I'm actually looking at. So here you can see actually there's this one's kind of nearby, taking up the frame. But we're looking at 3 different views here. That's a little bit hidden, but that's why. So you can imagine this as like top down, side on, and other side on. 3 directions. I feel like I've just made that much harder to picture, not easier. But that's what we're looking at. And so, yeah, there's a lot going on here. And you're like, oh, okay, so maybe, like, you can see this little bright spot at the center. That's really the galaxy we're interested in. So how do we get at just this without all this stuff around it? Well, that's what I've been thinking about for a while. And here's attempts to look at a bunch of different galaxies this way. Looking at different properties of them. Then I had an idea. So this is now just some galaxy. Ignore the thing above. This is some galaxy looking at from 3 directions, and it's a relatively nice one. There isn't too much going on. This is what happens if I look at only the density of stuff moving inwards. And it's basically the same. And this is what happens if I look at the density of stuff moving outwards. All of that substructure is sort of gone. Like going from this to this, we're arguably just moving to stuff with, well, we're just increasing noise. With here, it's just this. Like you can see hints of other things, but the density is, it's very clear. Let's make this small. So probably I need to reload the data actually at this point. So less grid. It's warm today. Ish. While this is running, I want to look up something else that someone asked me yesterday. BBC Bite-Sized Geography. Okay, I'm just going to have to watch it from scratch.
Our weather is in a state of constant motion. Sudden changes are hard to predict. In January 1998, on the south coast of Britain, The change in the weather was dramatic.
Coastal areas continued to bear the brunt of the severe storms, crashing waves battering much of the south and west.
What was he doing?
Over 100 miles per hour.
While the majority of people were taken by surprise by the storms, the Coast Guards at Falmouth were ready. Out in the Atlantic, a Spanish fishing boat, the Sonia Nancy, was struggling in the deteriorating weather.
We're getting reports that a Spanish trawler with 10 people on board is sinking in the Bay of Biscay. The vessel is said to be 200 miles southwest of Land's End. Falmouth Coast Guards.
The Coast Guards knew that the conditions were likely to get worse.
This is actually a very old-fashioned style of teaching, which is... I haven't watched the whole thing, but I do not care to keep watching it. Into 13. It's not displaying correctly, but well. Ah, interesting. So low pressure leads to unsettled weather. Because it's where warm air is descending. Loving the music. Now, I think this makes really good intuitive sense. It's just, do we have slightly less air than normal because it's leaving, or do we have slightly more air than normal because it's arriving? Air is, well, no, that really is what's happening, massive air. It's a bit of a lie that these tend to go in a certain direction in the northern and southern hemisphere. They do have a tendency to do that, but that tendency is relatively small and honestly doesn't really help people's understanding of these systems. No, actually I should check that before making a statement like that. I've been caught out by being overzealous with that statement before, but let's not be overzealous the other way. That makes no sense. So this is, you can see this as just saying that it's wet near the ground because the ground's covered in water and full of people, and so when that air rises it's taking wet air up. Even more so when a lot of air rises, air rushes in from the other side. The unseeability of pressure is something I find really fascinating. Like, it's busy doing its thing, but it's easy to misunderstand its thing because we can't see it. And this cell, please. Whoa, whoa, whoa. Maybe I was really lucky in the galaxies it was working for before, because this one, you can see the different sheet flows. So this one's really well behaved. God, I'm so impressed with it being this clean. Good on you, universe, but apparently it can be not clean if there is large scale flows. And look at it, all the stuff out here disappears. Let's have one final plot. Which is the stationary-ish stuff. Didn't plot it. So this is a very dense region. God, it still works beautifully. It really works. I'm kind of amazed that it works so well. Gonna keep thinking about this, but we'll be back in a sec. her turn. So, what do I do with this? One thing that's fascinating about this is it seems to pick out filaments really well. I'm just going to keep looking at some of these for a little while. Just going to get my head straight about what I'm thinking about here. It works so well. So in every galaxy we'd expect there to be some stationary particles because there's just a lot of variation of speeds of dark matter flow in galaxies. They're all going everywhere. So like it makes sense that we're seeing each other galaxy in these. Don't worry about these ones up top, they're not telling us really anything. Look at it! You can see when there's individual clusters, maybe. You've got to be careful about just so storying here, which I could easily be doing. So this is an interesting example where it works less. No, it doesn't. Works great. It's also interesting how it sometimes even compresses the plot, because there's just nothing up here that's moving outwards. So maybe I should explain a bit why, at least I think this is happening. Do I have... Yes. B? No. Actually be this size. No. Oh. Computers are gross. So I want to get the bottom corner of this. Oh. What if I put this over here? Will Chrome play better now? Yeah, that works fine. Except for... No, yeah, everything works fine now. It's just Chrome. Chrome is ruined. So, let's get rid of this bar. Aha, if you fill the whole thing with black, then the other is right. that broke it. Let's go with this. Let's just stick it. Yeah, my guide does not portrait. It's not a 4. You can see that. I'm having one of those mornings where it just feels like a lot to have to navigate something like this. It's not. It's fine. Okay. Pencil's fine. So, why is this happening? We have galaxies. Let's start with why galaxies collapse. So, at the beginning of time, oh, this is a very thin marker. That'll have to do. So at the very beginning of time, just click my screen a little bit. We have all universes in some box. So the universe is always in some box. And it's pretty close to flat. There's sort of equal amounts of material basically everywhere. But there's some regions which are have more material and some which have less. And so gravity starts to act. This region here, which is more material, starts to pull in stuff from outside. The universe doesn't necessarily have an edge. Drawing it as a box like this can be kind of misleading. Often actually what we do when simulating these is this edge is this edge, and so things are kind of pulling over the boundary. I won't get too worried about it now, but it starts to pull stuff in, as do all the other overdense regions. These regions are the things that will form into galaxies. Just because they have a little bit more, I'm not even sure if there is one down here, maybe it's a bit more like this down here. They just have a little bit more mass. So, can I like copy this? Are there more of these and they're just over around the other side? Okay. What if I magic wand it? Has it? Is it? Why? No, just put it here. Thank you. Oh, it's low res once you get down here. Didn't realise it came out pixelated. God, the time it takes to learn tools. If anyone ever tries to tell you that a tool is quick and easy to learn, they're probably not using it correctly. Okay, so let's have another box underneath this one. I'm not going to draw all the sides, we're just going to have kind of the main span. Not a very horizontal line. That's better. And so stuff has started to collapse to the point that now there's still some stuff everywhere, but there's some really dense regions. They actually don't really collapse like this, and I'll say more about this in a sec. And after a while, we have something like a galaxy at the centre, and it's still pulling in some material. We might have a kind of chain of galaxies. They're all pulling in some material. But after a while, they've kind of used up all the local material. I'm going to use a bit more, just one more layer over the top of this. Really push home these ones. And then let's really go for it in here. Just to show, like, yeah, stuff's really come together. So they're still collecting up material, but also they're starting to collapse towards each other because they're all gravitationally forcing each other. And if everything was left to just live out its ways, we eventually get to a point where you get really boring stuff, like still a tiny bit elsewhere, but most things have got together in some horrible galaxy at the centre, and it's not even got very much to pull in anymore, it's just kind of pulled everything in. Now this actually isn't the state of the universe that we tend to see, because the universe takes time to get this far, and even if it does get this far, if actually, so I said earlier that this box might be periodic, but let's say actually this is just a little slice of a much larger universe. There's always a bigger fish. And over here might be some whole constellation of galaxies. All orbiting around this central one. And that's going to pull in our guy. So there's this constant state of collapse, basically going under the simple gravity pulls stuff together. Early overdensities form. I'm just going to say form galaxies. We could phrase this in a ton of different ways, including saying stuff like they form the anchors from which we put together a view of the universe. And then these things keep on pulling in more material. Then these overdensities, oh, in fact all of these are happening all at the same time. This is not a one then the other. So this is, to use language that we tend to use, galaxies merge. Two galaxies become one. Now I actually think this language is a bit of a mistake, because galaxies, let's look into merge. What happens when you merge? So firstly, step one, you're too small. And thus, we can ignore gravity. Why am I including this step? Because it's always the first thing that happens. I'm going to move my head over. Then you get larger, just because you're constantly slurping up stuff. And you might be being slurped up if you are a particular galaxy. And this is, well then honestly I don't know how to start on talking about it, but it's the most important thing. You become massive enough to be bound. And what I mean by bound is gravitationally bound. And what I mean by gravitationally bound is, ask me about it later. You start to move towards each other. This takes some time. I don't know why these are here. And then step 8, you might be thinking like, oh, they fall together, but no, now they get close enough that they orbit each other. Because we're dropping a big thing that was moving this way, and over time it's kind of drawn off track. It's moving over here towards another big thing that was moving this way, and over time it's drawn off track to moving over here, and you end up for a long while with some kind of orbit. The massive one tends to move less, although that depends on the thing. You have a long period of this. Slowly lose energy. Sink. Together. There's two ways of teaching physics, and one of them is bad and is what's done most of the time, and the other is good and is done for most students, but later. And it's whether you talk about forces or energy. We should teach physics talking about energy. Forces are the way energy transfer processes act. But they're not kind of a fundamental thing. It's the energy processes that are the fundamental thing. And then eventually, one So that doesn't explain why this is working so well. It's just a different thing that I decided to explain because, I don't know. Sometimes I just explain stuff. Don't sue me. Oh, look at them! I love it. It's so good. I'm really surprised by how well this works. You might be watching this being like, oh, that seems like you turned one mess into a different mess, which is true, but that one's not so good. So why is this happening? Well, let's say we have our relatively large galaxy. This has been here the whole time, hasn't it? And it's still got some stuff around it. Maybe even some of that stuff is other galaxies. Because often things will tend to collapse on smaller scales first. In fact, the math of this is fascinating and I love it and I recommend it. Things reach the condition that collapse can happen on large scales, and then smaller things collapse quicker, and as the larger collapse happens, those smaller collapses happen, and this is why you get one galaxy filled with billions of small stars. But anyway, the whole time, this galaxy is sitting here and it's just hoovering up mass. Because if we look at some individual particle, maybe it's on some straight trajectory, maybe it's on some kind of liney trajectory, but it's colliding with things, it's making some random path, and eventually it just slips close enough that its velocity becomes less than the escape velocity of the galaxy. What's the escape velocity of the galaxy? That is the velocity needed to fly away, basically. Why is it a particular velocity you need? Well, because energy is the most important process. You can set your 0 point for energy in different places, but this is where the energy is less than some escape velocity, which means that the kinetic energy is less than some potential needed to escape, which means that I should use a U for this, so I'm not doubling up. No! Some potential needed to escape, and because the kinetic energy is a function of the velocity, that means that V is less than your fiducial escape velocity. And so it drops in. And it probably drops in on some kind of orbit, because it's got some velocity. This is a bad drawing, but it just happens to have some velocity not pointed directly towards the centre of the galaxy. This is happening all over the place, and some of it goes straight in, but most of it comes in with some sweeping orbit. So this is happening all the time. Stuff, you could even draw a kind of rough edge. It's rough because it depends on like what the speed of stuff around this is, but you could draw some rough edge and all this stuff falls in and it starts an orbit. And if it was orbiting a stationary galaxy, a kind of perfect point mass, its orbit would look something like this. Just go round and round, sort of Keplerian-ish. We're saying it doesn't really like hit the high mass stuff in that. This isn't quite true, but it's roughly what happens. But there's an issue, which is when it leaves here, so t equals 0, and then it gets round to here and it's at, let's say t equals t1, but at this moment, the galaxy's got bigger. The mass at T1 is greater than the mass at 0, so now the orbit is actually smaller. So let's call this T2. Mass at T2 is greater still than this, and it never gets as far out as it did on its first passage. So if we draw this in kind of regions, we have the galaxy, we have our rough edge that I'm going to call the infall radius, where stuff is able to go through, but because the galaxy is growing all the time, to use the terminology of the moment, the splashback radius, the distance, the radius of first apocenter is smaller than the infall radius. So stuff falls in here, goes on some path, and comes out to here. And that difference is just based on the fact that over that time, the time it's gone on this path, the galaxy's got more massive. But that means that stuff goes this way through this region. You know, it can be going this way, it can be going this way, but it's always going in. But stuff moving outwards never really leaves this region. There's plenty of stuff moving inwards here as well. Stuff's moving in all directions in here. But this is getting a little bit busy. So let's simplify it again. Here we only have stuff moving inwards. We might have some stuff that's basically stationary. That's uninteresting. And here it's moving in all directions. So this is the region we're seeing here. This is stuff moving outwards, and it doesn't exist out here. Or at least, like you can see, these pictures are more busy than what I've drawn here. I don't have a nice pair of circles because there's a lot going on in the structure of the galaxy. Oh, I love this. This is capturing large-scale structures so well. Look at it! And it also captures this bit out here. So where have we got these stationary bits? Oh, actually, I gotta go. I've got a meeting. Let's really quickly talk about why we have these stationary bits. Ooh, not bad. These stationary bits are happening because actually, when we have in 3D this initial random density, yeah, probably does look something like that. You can see there's kind of a spine here of massive stuff, of more heavy stuff, and we'll jump a step ahead. The first thing that happens is stuff is attracted to the spine. Like the forces towards the spine are a lot larger than the forces along it. Although there might be a massive thing here, the gravity that these things feel is basically just towards the spine, and so we get a lot of mass coming together along here in a bit of a sausage, basically. It then quickly collapses in the really overdense regions into individual galaxies, and all the while it's collapsing everywhere, so that this sausage becomes kind of rough. That's why, although we can see really clear shapes, like here, this long stationary bit really shows out up clearly. It's still really kind of patchy and all over the place, and you can start drawing kind of the extended bits where this stuff is stationary, and you get shapes that look like this. Anyway, so that you just turned up, and I am about to go. I have a meeting. As I often say, I will maybe be back later. 50-50 I won't, but we'll see. See you then.